Hello everyone, Mr. Fawcett here, and we're back with another geometry lesson. Today we're going to talk about shortcuts for proving triangles congruent. So if you think back to lesson 4.4, we said that there were 6 things you had to prove about the two triangles before you could say that they were congruent. There had to be 3 sets of congruent sides and 3 sets of congruent angles. Today we're going to talk about 2 combinations of 3 of those things, where if you just prove those 3, that's good enough to say that the triangles will be congruent because it holds for every possible pair of triangles that has those characteristics. So it's going to shorten our proofs a little bit without diluting any of the math. So let's get started by working on these 3 warm-up problems. Pause the video, take a minute or two to do these, and then join us for a discussion. All right, so the first question says, name and draw the angle formed by ray AB and ray AC. Here's ray AB. And here's ray AC. Of course, A is the vertex of this angle because it's the shared point between the rays. We could name this angle. We could just say angle A because there's only one angle around vertex A. We could say angle BAC, and we could say angle CAB. Of course, the similarity is that A is always in the middle because it is a vertex. Name the 3 sides of triangle PQR. Well, if you want to sketch it to help, that's okay. So I'd have side PQ, side QR, and side PR. And number 3, we have a triangle congruency statement. Triangle QRS is congruent to triangle LMN, and it says name all pairs of congruent sides and angles. So let's run through these real quick. We have angle Q congruent to angle L. Remember, the angles that are congruent are going to be in the same corresponding spot. So the first spot and the first spot, right? Then we have angle R and angle M because they're both in the second spot. And finally, we have angle S and angle N because they're both in the third spot. As far as sides go, same idea. Corresponding sides are going to be the congruent ones, so the ones in the same spots. We have segment QR is congruent to segment LM. We have segment QS congruent to segment LN. And finally, we have segment RS being congruent to segment MN. So again, just match up those letters. That'll help you figure out the corresponding sides and angles, which will be the congruent sides and angles. All right, before we get to the shortcuts, let's first review what congruence means when we're talking about figures. So 2 figures are congruent if and only if, right? That's a biconditional. Let's get a different color. 2 figures are congruent if and only if they can be mapped onto one another using a series of rigid motions. So that's our definition of congruence. We can map 2 figures onto one another using a series of rigid motions. Hopefully we remember what those rigid motions are. We've got translations, rotations, and reflections. So here's what we're going to do. Before we can use these shortcuts and proofs, we have to prove that the shortcuts themselves work, or at least we're going to do that for a couple of these. So the first shortcut that we're going to prove is SAS congruence. And SAS congruence stands for 2 triangles where there's 2 sets of sides that are congruent, and the included angle between those sides is congruent. All right, so we have these triangles not mapped off like this, ticked and arced off like that. So that represents side, angle, side. Again, the angle has to be in between the 2 sides. Now, what we want to prove is that if we have any 2 triangles, right, it doesn't matter whether they're, acute triangles, obtuse triangles, right triangles, triangles whose sides are, inches, triangles whose sides are centimeters, triangles whose sides are even miles. right? We don't care how long the sides are or how big or small the angles are. As long as they fit this criteria, right, where they have two sets of congruent sides and one set of congruent angles, well, those triangles will always be congruent, right? So that's why there's no numbers on here telling you how long the sides are, how big the angles are, because these triangles represent any two triangles that we could draw that have two sets of sides and one set of angles being congruent. So if we can show that these two triangles are congruent, we will have proven that any two triangles with these characteristics are congruent. And then we can use a shortcut. All right, let's think about this question. It says, given our definition above, what must we do to show that these triangles are congruent? And we are not allowed to just say that they look congruent. So think about what the rigid motions are. Maybe you want to actually say, okay, I think we need to use this rigid motion, or maybe we need to use both of these rigid motions to map one triangle onto the other. And we are going to say we're going to map the pre-image onto the image. So think about which one's the pre-image. That's got to be the one with no primes. That's going to be this one. So how could we map the pre-image onto the image? Go ahead and take a second to think. All right, so we're actually going to have to use all three types of rigid motions here. And I'm not going to go through all the different possibilities because we'd be here all day and I want to keep this video somewhat short. But we're going to have to use a translation. We're going to have to use a rotation, and we're going to have to use a reflection. So let's walk through these on the next page, see what order we have to do it in, see what they look like. Okay, the first thing we're going to use is a translation. And we're going to map the two vertices together that are the congruent angles. So we're going to map A onto A prime, because those are the two angles that are congruent. Once we do that, we can see that we get this image over here, right? So we haven't rotated, we haven't reflected. All we've done is shift the left triangle down onto the one, or down to the right triangle. All right, the second thing we're going to do is use a rotation. So you can see that down here. And we're going to rotate until two congruent sides are mapped onto one another. So notice that you could rotate either way, right? They're starting over here, right? They're mapping C onto C prime. And that's what gives us this diagram over here. However, they could have done it the other way as well, right? They could have actually rotated B onto, oops, I need my pen. They could have rotated B onto B prime, right? And they get a triangle that looks like this. So C would actually be over here, and B prime would then be the same point, right? So either way, you can do it either way because there's two sets of congruent sides. We'll just go with the one that they had, where they've mapped side AC onto side A prime C prime. So we're currently right here. Well, I think it's pretty easy to know what the last thing we'd have to do is, right? If I want to map those two on top of each other, I'm going to have to use a reflection. And I'm going to have to reflect it over the line AC. If you can't see it, it would be this purple one right here. Right, if I reflect it over, A and C are going to stay right where they're at because they're on the line of reflection, and B is going to hop over to B prime. So when that whole triangle flips, they're going to be mapped right on top of one another, and we have just proven that they are congruent. Okay, so we've now just proven SAS, which is cool because now in a proof, if we can prove that just two sets of sides and one set of angle are congruent, well, we can stop right there and say the triangles are congruent. We don't have to go and prove the other set of sides and the other two sets of angles. Down here, they're just showing you that even if the triangles were situated or oriented or positioned differently, we could still use a series of rigid motions to map them onto one another as long as they fit the initial characteristics for SAS, right? As long as they had two sets of sides that were congruent and one set of included angles, we could eventually map them onto one another. So we're not going to do this on the video, but you could take some time and write down, right, if the triangles already looked like this right here, what would be the transformation needed to map them onto one another? Same thing if we were down here. What transformation or series of transformations of rigid motions would we need to use to map those triangles onto one another? So again, they're just positioned a little bit differently. It's actually a little bit easier because they've already done that translation for you, so you're either going to choose reflections or rotations. All right, let's take a quick look at the SAS postulate. So if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. All right, so if you see a diagram like this, then you can automatically write your congruency statement without knowing anything about the other sides and angles. I want to do a proof with this postulate first before we get to SSS, so you really have an idea of how useful it can be. So we're going to go down here. We're going to go down to number 2 right here. And you'll notice that this is a short proof because we're going to be using a shortcut. So we are given that side XZ, segment XZ, is congruent to segment VZ. All right, those are already ticked off on our diagram. We're then told that segment YZ is congruent to segment WZ. Those are ticked off with 2 tick marks on our diagram. And we are trying to prove that the triangles are congruent. So we're trying to prove that this blue triangle is congruent to this red one. So let's read our statements. Well, the first one's just a given. And notice that this would be like 2 little s's, right? We've proved 2 sets of sides congruent. Well, the next statement deals with angles. Angle XZY, it's going to be this one in blue, XZY, is congruent to angle VZW. Well, that's this angle in red. Well, what's a reason for why those angles are congruent? What's the property, theorem, postulate, etc., that makes those angles congruent? Well, it's going to be the vertical angles theorem, right? They're formed by 2 intersecting lines and they're across from one another. Vertical angles theorem. And this would be a little a. So we've proved 2 sets of sides and 1 set of angles congruent. And it's important that that angle was in between the sides, right? It wasn't one of the angles out here. It was the angle in between the sides. So because we've done that, we can jump right to our congruency statement. We can say that triangle XZY is congruent to triangle VZW. And our reasoning is SAS congruence. You can just leave it as SAS though. That lets me know you know why those triangles are congruent. So you can see this proof is a lot shorter than it would have been in our last lesson. And this is only one of the shortcuts we are about to learn. We're going to learn one more in today's lesson. This lesson is going to go a little bit longer, probably close to 30 minutes, but I'm just going to squeeze everything in one. So now we're going to talk about SSS congruence, or triple S congruence. We're not going to go through the proof because we already did a proof for SAS, and again, for the sake of the length of the video, we're just going to talk about what SSS is and then look at how to apply it. So SSS, if three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. So essentially, we don't need to know anything about the angles as long as we know that the three sides of one triangle are congruent to three sets of another. All right, that is going to be good enough. So let's do a practice proof just like we did for SAS, and we're going to do another short one, number 1. It says, given that segment PQ is congruent to segment PS, those are labeled with 1 tick mark, and segment RS is congruent to segment RQ, labeled with 2 tick marks, can we prove that triangle QPR, let's do that in red, QPR is congruent to triangle SPR? Well, we already have 2 sets of sides that are congruent. And, well, let's actually fill that in as a given. Put a little S here, a little S here, 2 sets of sides. And then our next statement is that PR is congruent to PR, those 2 segments. So we can put 3 tick marks on PR because it's a shared side, right, of both triangles. So segment PR is the same. Well, what do we call this? What is the property or theorem or postulate or definition that says something is congruent to itself? Well, that's a reflexive property. And in this case, property of congruence because it's a congruency statement. All right, well, that's a third little s. Now we have enough to prove the triangles are congruent by SSS. So again, these 2 shortcuts make our proofs quite short, right? Because we're only having to prove half of the things that we did before. So there are more shortcuts. These are the only 2 we're going to use today, SSS or SSS and SAS. Let's go look at a few more different types of practice problems, and then we'll wrap this up. Let's do number 1 for these 2 diagram problems. So it says, is there a value of x that makes the 2 triangles congruent? Make sure to check the value works for all sets of corresponding sides. Then write a congruency statement. So we have one triangle with all 3 sides labeled as just numbers, right? Triangle UVW has sides 2, 3, and 4. And our other triangle has expressions for each of the sides. So it doesn't tell us which sides are corresponding. So we may have to just play around and hope we pick the right combination. There is a way to check, though, at the end to make sure that our x value is the correct one. I am going to look at how they're drawn, right? So I'm going to look at what seems to be the shortest side of both triangles, and we do have to be careful, right? These may not be drawn to scale, but I'm just going to start with these 2. So if these triangles are congruent, well, all 3 sides, there has to be 3 sets of corresponding sides that are congruent. So I'm going to assume these 2 are congruent to start with. So I have 2 is equal to x minus 1. Add 1 to both sides, I get 3 is equal to x. So let's assume that x equals 3 and see if the sides over here will all be the same as the sides from triangle UVW. Well, if x is equal to 3, then I have 3 minus 1 is equal to 2. Okay, checks out for that side. But we knew that because those are the 2 sides we set together, set equal to each other. Let's look at these 2 sides. Okay, if I have 3 times 3 minus 5, well, that's 9 minus 5, which is equal to 4, which works. Let's check our last set of sides. Well, I know that x is equal to 3, right? So I don't have to do any work. I just substitute that right in, and both sides are equal to 3. So that value for x is equal to 3, is going to work here. Now we have to write a congruency statement. So I need triangle something 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 is congruent to triangle something something something. Well, we don't have any angles given, right? We can't just match up the arcs. So we're going to have to match up the sides. Now I'm going to put some tick marks on here for the corresponding sides to make it a little easier for us. Let me choose U for the left triangle. Now U is between the side that has 3 tick marks and 1 tick mark, right? So I'm going to go over here to the other triangle and choose the choose the vertex that is between the side with 3 tick marks and the side with 1 tick mark, and that is Y. So U and Y are going to be congruent angles. Now I'm going to choose V. V is between the sides with 2 and 3 tick marks, which is the same as X for the other triangle. X is between the sides with 2 and 3 tick marks. Well, there's only one option, right? It's going to be W. W is between the sides of 1 and 2 tick marks, and Z is between the sides of 1 and 2 tick marks. Remember that your congruence statement may look a little different than mine, right? There's several different ways we could write this. As long as my letters are in the same corresponding positions, right? So U and Y have to be in the same spot, but I could put them both second. I could put W and Z both first, and I could put, can't put them in the same triangle. And then I have V and X in the third spot. Notice that, right, U and Y are still in the same position in both triangles, right? They're first in the first statement, they're second in the second statement. Then we look at V and X, and V and X. Second place in the first statement, third place in the second statement. And then we have W and Z, third place in the first statement and both third place in the first statement and first place in the second statement. There's other combinations that we could do, right? As long as those letters both match up, right? So U and Y always have to match up regardless of what spot they're in. All right, let's do one other type of problem. We're going to do some of these, 1 through 5. So it's to state whether the triangles can be proven congruent using SSS or SAS. Explain why or why not. If they can, write a triangle congruency statement. We're going to do 1 and we're going to do 2. 1 and 2. So pause the video, take a minute or two. Could you use SAS or SSS for either of these two sets of triangles? If you can, try to come up with the correct congruence statement. All right, so for number 1, right, we currently have one set of congruent sides and one set of congruent angles. The problem is that is not a shortcut, right? One set of sides and one set of angles. So we have to see, is there any other set of sides or well, in this case, we'd have to use a set of sides, right? Because it's got to be SSS or SAS. Is there another set of sides we could say are congruent and have a reason for it? Well, what about this shared side, right? That's a side of both triangles. We do have a good reason for that. We can say segment AL is congruent to segment AL by the reflexive property. Then we have two sets of sides and one set of angles, the included angle, for both of those triangles. So I can do triangle ALS LE is congruent to triangle. Now this is, we have to be careful here. Maybe it's easier if I erase. Notice for the triangle below, I'm just going to point to it in red, point to the other one in blue. For the red triangle, angle A is the angle that has the arc. It's also between the sides with 1 tick mark and 2 tick marks. So for the blue triangle, that's going to be vertex L. You know what? It's probably easier if I color coordinate this, I assume. So we had ALE, and then for the blue, we have to start with L. If my second letter for red is L, well, for L, L is on the other side of that segment with 2 tick marks, right? If we're talking about the red triangle. So here's my red triangle. L is on the other side of the segment with 2 tick marks, the side that doesn't have the angle arced off. For blue, right, that would be A. A is on the other side of that segment with 2 tick marks, and it is not the angle that is arced off for the blue triangle. And then, if E is the last letter for the red triangle, right, it has to be P for the blue, because that's the one that hasn't been used yet. But you could also see that those are the 2 corresponding ones on the figure as well. All right, so that would be our congruent statement, along with our reasoning why segment AL is congruent to segment AL. We also should put that this one is SAS, side, angle, side. All right, moving on to number 2. We're only given one set of angles here. So we'd have to come up with like 2 sets of sides or 3 sets of sides if we're going to use one of these shortcuts. Well, I think we see the obvious set of sides, right? That's right in the center with the reflexive property. But is there a way to prove another set of sides congruent? In this case, there's not, right? There's no other reflexive property. There's no midpoint being given. There's no segment bisector. There's no reason that we could say why any of the other sets of sides are congruent. So for this one, we would say can't prove congruent. We don't have enough information. Okay, we are going to end it at this point. Again, big takeaway from this video is that there are several shortcuts we can use to prove triangles congruent. We'll come up with some more in the next video, but from this video, we can use SAS, so side, angle, side, where the angle is in between the 2 sides, or we can use SSS, side, side, side. All right, enjoy the rest of your day, and I look forward to seeing you next time.